Hey, hello everyone. Welcome to our last lecture of this quarter. This quarter went by pretty quickly or slowly, depending on how you see it. But we're finally going on to topics that are related to your next lab. So there's a lot of large announcements I'm going to try to grind through today. And if you guys want to look back on it, it'll look back in the recording for the details. There's like 4 pages of this, so like get ready. So first thing is shipping and lab due dates for the upcoming labs. So in terms of shipping, we're going to be shipping your parts on Thursday. We already finished the boxes, and wait, on Monday. Why did I say on Monday? I think that was my brain, but we should be expecting to receive it within like a day or two. So it's like Friday or Saturday or Sunday or something. But yeah, like before Monday for sure. We're gonna publish a list of your lab parts that everyone should have. And this does not mean like your SMD components and things that we're shipping out to you as well. This just means like your MCU, your IMU, certain things like that. We expect to receive all of these back by the end of the year. So, and that will be everything on the list that we give out to you. Except for wires, we don't really care about wires, but we would like them back still if you could. So one, you should keep the box it was sent out in just to make it easier for us. 2, make sure that as soon as you get it, try to take an inventory and reference it with the list of the lab parts to make sure that you aren't missing anything. If there's a part missing by Wednesday of next week, and if you guys didn't tell us that you didn't receive the box or whatnot, then it's not our responsibility anymore to replace it because you could have just lost it halfway through. So you may lose money off your deposit. So, but if you tell us beforehand, then we can just replace it for you. And the last thing is just to check if your custom parts are received. Just check your BOM. Some of your parts have been changed and we've messaged teams individually. So it's not on your, but we haven't changed your BOM. So just keep that in mind. We don't need to receive your PCBs and SMD components or drone frames at the end. So you can keep those indefinitely. Okay. In terms of due dates, so the schedules that we had before are completely off now because we delayed a lot of the PCB things. So the checkpoint 1 will be week 8 on Monday. Oh God, if you guys don't get it in time, maybe not. Maybe it'll be like Wednesday or something. I'll change this. I think it's going to be Wednesday. I'll change the slide after. Checkpoint 2 will be on week 10 Monday. And then all due dates, make sure it's before 6 p.m. that day because I don't want to be checking you guys off like at 11 p.m. or something. The due date will always be correct on the lab spec. So some things that I post a lot of due dates on the website, whatnot, on the slide. If things change, the lab spec will always be right. The lab will be posted soon. You guys won't need it until you get your parts. I still need to make some changes, and hopefully tonight, if I'm not too tired after lecture, I'll finish that. But definitely before shipping. Oh my God, I meant before shipping, not after shipping. I was so tired of writing this. Oops. But yeah, definitely before shipping, you'll get your lab spec out so you guys can start that. So the way that checkouts work now, you guys will each have your own set of hardware. We're shipping you guys individual stuff so you can all work on it. You guys are allowed to share code and actually and use the same code, and we encourage you to do that. And we fully expect you guys to work together on this. So if you come and you have the same code, then that's like completely normal. But you guys should all be engaged with working on your own hardware and running it there as well, and on your own computers. So during your checkoffs, you guys must demonstrate that you've completed the assignment. So keep your hardware connected. Well, you'll definitely need that to show us your results. It's possible that we might not check certain individuals off who don't show up, or if their teams say they haven't been participating, or if you don't answer the questions that you definitely should know. And we might have to delay you checking off until you demonstrate you've completed it. And lastly, there will be checkoff questions. So it's kind of like the first lab we had. So you'll need to come to lab to show stuff to us. Oh, and in terms of parts, there's going to be 2 parts. Your checkpoint 1, checkpoint 2. Within those checkpoints, there are actually like multiple levels that you can come get checked off if you're unsure about things. Okay, in terms of soldering and ordering stuff, this is more something on you guys as opposed to logistics on us. So Aaron and I have decided that basically, since most people indicated that they're willing to order their own things, because if we were to give you the bare minimum, one, it'll be a lot more expensive because we have to ship and whatnot. And it's just on and off for like some people want to order their own better ones, some people won't. So we thought just to keep it fair, basically everyone's buying their own. However, if you're unable to or you are not willing to buy your own, then you can, if you communicate this to us, we may be able to still, we'll probably be, if you just talk to us about it, we'll be able to return all your deposits back to you as if you've completed everything, as long as you complete the labs as well. But of course, just for your own experience, we encourage that you get your stuff. The thing that you'll 100% need, and this is basically like, if you can get this, then we will continue on. And that is you need a soldering kit. It'll, I saw on Amazon, it's like $17 to $25. This includes like everything from iron solders, so solder wicks, solder suckers. I guess it includes like a lot of stuff. So you'll definitely need that one. You should order as soon as possible, just so you have it, and you won't, get behind on that. Things that will make your life a lot easier. One is a heat gun, and when you Google it, you should Google like soldering hot air gun or something, and you'll need solder paste to make that work. That'll be like $40 plus, but I've seen like it combined with soldering irons to make it like $60 or something, or like $55 or something. So it might be cheaper if you buy it with the soldering iron too. The last thing is a MIDAC. It's not like completely necessary, but it makes your life a lot easier. As I said before many times, you're gonna need it for future e-classes, I guess required, and you can easily sell it for $200 when you're done. So it's expensive, but eventually you'll probably end up selling it anyways. And if you don't get this, I will suggest that in your soldering kit, get one of the soldering kits that has a multimeter on it, because it can replace some of the functionalities of the MIDAC.
One thing that I think is worth mentioning is that, so for some of the team's components, you guys will actually like need a heat gun and solder paste because you have pads that are like below the component. Like for example, some teams VRMs and stuff. In order to be able to solder, you actually may need a heat gun. And I think some components also have hidden pads as well that require heat guns to solder. And with regards to the MIDAC, if you're in Westwood, you actually might be able to purchase one secondhand from someone for like even cheaper than 200. Like last year, I got my DAC for $100. Like it didn't come in a box, but like I got a plastic bag with like all the probes and stuff. So you can probably find even better deals than $200. Joshua asked like, what's a MIDAC? So a MIDAC is, I think it stands for like Data Acquisition System. It's made by like National Instruments, and it's they have like their own proprietary software where it's like a it's basically a multimeter, ammeter, and a bunch of like other like functionalities all in one. It's also its own like it can be a function generator. I can't think of like what else it can do.
The big one is being an oscilloscope, because
yes,
if you have just that's a big difference between that and a multimeter in our usage. And because if you're like outputting I²C, you can actually see the individual bits you're outputting using an oscilloscope, but you can't see that with a multimeter.
Yeah.
So that will help you a lot in terms of debugging that.
Typically, if like school were in person, you'd be able to like drop by the lab and just actually bust out like a whole scope, but we obviously can't do that. So we recommend like a MIDAC will be sufficient if you actually did need to debug your board.
Yeah, that's the other thing. If I know that there's some of you guys who are near campus and you might be watching the recording of this, but if you're on campus and you communicate with us, if there's like a day you want to go solder, you can tell us that. We can let you into the lab, so you don't have to buy this stuff yourself, and you can just use the lab stuff. Although I will say it's very messy in there because it's just been officers using stuff. So yeah. Other logistics. 3D printing. We recently, like our plans for 3D printing have changed because the person who's going to print for us wasn't in Westwood. We ended up having to find a way to order 3D printed things. If you have a 3D printer, you can print the drone frame for yourself. Instead of us doing it for you, then we don't have to ship it. It won't like likely break or anything. And also you can make modifications and it's more fun. So tell us if you have a 3D printer, then we won't order for you. In terms of PCB stuff, we're finally pretty much done with it. Final PCB edits do this Friday. Some teams we have like a separate deadline. I said I want to look at it once more. You'll probably have some like tiny like tweaks that take like 5 minutes. I'll be online Friday for those teams. If you're done, then I can review it for you on the spot, and then if you make changes, we can finish up at night, and then me and Aaron can order on Saturday. Cool. Logistics. Any questions about that?
Before we begin the actual lecture. So the parts have already been ordered. We're just waiting on. Oh, so Tim asked, like, are we ordering parts Thursday or this weekend?
Oh,
we already ordered all of the SMD parts. We're just waiting on ordering your PCBs.
David, anything's fine. By the way, he direct messaged me, but yeah, anything's fine. Yes. We'll check after. We might, if people are having trouble finding stuff, we can get you guys links actually. But yeah, it's just some people would want to order better ones that are like maybe like $5-10 more expensive. Some people want to go for the cheapest one. So
damn, $100, David. Oh my goodness.
Balling. Yeah, and in terms of this, the thing I said this Thursday was because I used to want to check you off beforehand to have another day, but your board ended up being really good, so you don't really need to. Oh, post last week's lecture. Yes, we will. We will. Okay. We'll post them all today because that all accumulates into this next lab. So yeah, we'll do that. Cool. Oh wow, Aaron, you added like animations. It was amazing.
Yes.
Cool. We're talking about feedback control today. Some of you guys might have heard this, some maybe not. And basically here, we'll just talk about what control systems are, right? So 2 ideas of what control systems are. There's this open loop and closed loop. And that's kind of what you immediately introduce to when you take 141, which is a control systems class. Or if you take it, it's an elective. But well, the difference between these two, and here's the easiest way to think of it, is this analogy of having a toaster oven and like a meat thermometer thing. What a toaster oven is an open loop system because you have an input of like, for example, like, oh, you want it to cook to like this level. Then your controller says, okay, if you want to cook it to like medium heat or something, or like medium brown or something, then you put it at for like this temperature, this time. And then it just does the thing and then outputs whatever it is. Now, you can never really get exactly what you want because you kind of have to test it. You don't know exactly how hot your toaster is, what kind of bread you have. So your output is very susceptible to certain noise levels that are introduced into your system. On the other hand, what feedback control is, which is also what closed loop means, is instead of just doing that, you also have a measuring element that goes backwards. So if you're cooking a steak with like one of these fancy thermometers, then you never would just look at put it for a certain amount of time and then say, okay, it's done. You measure it and wait until the measurement reaches the point that you want, and then you take it out. So your process and your control signal is dependent on what measuring element you use. So the problem here then is when we're pretty much everything in the world right now is kind of controlled like with closed loop, like ACs for whatnot, like everything is controlled with closed loop. But drones especially, we have to use some kind of feedback measurement because if you want to like turn left, it's not about turning left relative to your drone's frame. It's always like tilting to a certain direction relative to the global frame. So we have to use sensors to determine the quadcopter's true orientation, like what angle it is referenced to the world. And this will be fed back into how we control our motors. So first, some review. I'll try to zoom through this because we talked about this a lot. I2C, this is how we're communicating with our accelerometer and gyroscope, which is all in your IMU. 2 data lines, open directed protocol. Yeah, we've done through this. It's synchronous, and this will just be useful for your lab because you'll have to implement the code for this. And also the initialization. So in terms of protocol, you always have a start bit. You have your bits for your address to tell to say which module you're communicating to, and then read or write. Then you have your data and your data frame, which is often, depending on the module, going to be the register address and then the actual data that you're putting in. Yeah. Cool. Any questions about this so far? Okay. So first thing we're talking about is gyroscopes. What gyroscopes do is that immediately what you know about gyroscopes is they output some measurement that is related to your angular velocity. So if you have something that is rotating at a constant speed, it will output a constant value. This is kind of how you can think of it. Gyroscopes actually are physically very complicated. They revolve around these like vibrating bars that I really don't understand. But this is just how you can think of it. It utilizes centrifugal force and internally converts that into the angular velocity because it's directly related. They use a reference vector to determine the orientation. This is just how we represent angular velocity, because you can't really say like x, y, or z, and it's really hard to convert it into like polar units or something. So the way we do is we represent it as the axis of rotation, and we use the right-hand rule to say which direction it's rotating. So for example, here, and if we want to represent this gyroscope rotating this direction, then you would have it in the rotation vector to be this way, but it's actually rotating along like this circle with the right-hand rule. And the larger the vector means the faster the velocity. So some of the problems with gyroscopes that we have, one is very theoretical and took me a while to wrap my head around. If you guys could like act like legitimately, especially since your cameras are off right now, this is like how I really figured this out too, was if you literally stand up right now, okay, and then turn to your left, like 90 degrees, and then imagine like falling face down, and you'll be facing that way. But if you go face down and then turn to the left 90 degrees relative to your own frame, you actually are in a completely different orientation, right? So what this tells us, and you can see with this book diagram, you can look at it after with the lecture slide or with the recording, that if you were to rotate it along a certain axis and then do the exact, its own axis, that being, since when we're controlling the drone's motors, it's always relative to the drone's axis, it's not commutative. So the problem with this is that when we represent, if we had a perfect idea of the continuous like axis of rotation, then everything is fine. But since we're working with like discrete values, we have to assume that these two rotations sum up the same way. So we actually can't know if it rotated like x first or y first or z first, for example, or if in that order at all. And these errors can slowly add up over time, which creates inaccuracies in your reference vector. So that's one of the problems with gyroscopes. The second problem is that there's just noise in general with your gyroscope. Since you're using like a certain resolution for the values you have for your angular velocity, you always might be like 0.0 something off. So when you're adding these up over time, because in order to find the position of your drone, you have to add up these velocities, right? Like you're integrating velocity to get position. You end up creating this thing called gyroscopic drift, and this is a very important concept in like spatial sensors, in that your reference vector, which is the integral of like your angular velocity, will over a long period of time, the noise will always add up. So the way I think of it is if you had like an integral of your like velocity and you plus some noise, your noise will be like noise times time, and then it will just, create a lot of drift. This is why you never really integrate accelerometers to like find your position, for example. So it creates really accurate measurements for both high and low frequency movements. So just like, I'd say like high and mid frequency movements, but only in the short term. So if you have the longest frequency, which is a longer frequency, that means you actually have to take it over a longer period of time. Like I probably said this before where, could you approximate it by dividing the rotation into small steps, calculating? Yeah. So that's exactly what we do actually. If you have a very fine grain like measurement, that's exactly what we do. We estimate that, let's say we have like x rotation is equal to like 1 like degree per second, y is 1 degree, z is 1 degree, that it's all happening in the sum of the, like, if you sum up those vectors, that's the new axis rotation. But that's actually not like the real rotation, right? Because during that time period, your gyroscope was not like, it wasn't a single axis. You know what I mean? Does that make sense? So if you have like a really bad gyroscope where the time period between your samples is very long, then it could have moved in like a whole bunch of axes and you wouldn't know. So your estimation becomes more and more off. Anyways, so yeah, so for the lowest frequencies, we start to introduce gyroscopic drift. And that's because if you think of like the lowest frequency, that's DC, and that's just like a constant value. And you take it for your gyroscope for a long time, then there's going to be a lot of gyroscopic drift. So the way we're going to deal with this is to correct it using another sensor, which you probably guessed by now is, wait, yeah. Yeah, so it's the accelerometer. As we kind of talked about before in the last lecture, accelerometers, they determine your orientation by measuring the net force. And specifically what we're trying to extract from this is the net force due to gravity. It's made with materials that change conductivity with pressure, or sometimes uses some like capacitance. So if you change the distance of your capacitor, it'll create some capacitance. Oh shoot, sorry. It's your slide. Go, go, go.
Yeah. Actually, I was going to mention one more thing with regards to gyroscopic drift. If you guys like use like, I guess, like play video games that kind of require accurate mouse movements, there's also something called mouse drift that's very similar to in concept to what gyroscopic drift is, where depending on like the rotation of your mouse, certain movements don't translate perfectly in like all axes, so you eventually get like some form of drift as you use your mouse in like said games, right? So that's just like an analogy of like of what that is. You can look that up too. But yeah, so with regards to the accelerometer, Eric basically gave like a quick rundown where like we determine the orientation of the device itself by measuring the net force with its movement. We also cover this a little bit in the previous lecture that will be uploaded soon. But it's made with materials that where as you move it, like this central like mass will like push against a certain surface, and in this example it's a piezoelectric material, and as it pushes down it'll change the conductivity of the material. And we in our case, the accelerometer, you kind of extend this model into 3 dimensions. So as that central mass moves in 3 dimensions, it'll change the conductivity of the different surfaces in like a 3D space as it moves around. And you guys might remember this example from last lecture. So our accelerometer, it takes readings from a free fall reference. So like gravity isn't included. And so as you can see on the left, in free fall, like if it were just like, if you just dropped it, the readings, and you were able to collect the readings, it would essentially report that there's like no acceleration, right? But then at rest, it will point upwards, since that's like where, since if it's resting, then like the force is up, like normal force, right? And if it's like rested and slightly tilted, then it'll point in whichever direction that it's like quote unquote upright. And so then we get to the issues of accelerometers. They're very susceptible to like error when it comes to jittery movements. So in this example down here, you can see that, so PD stands for like, I think it's an example of like Parkinson's, right? Where like you kind of, you get like uncontrollable like shaking movements in your extremities. So you can see right here that like in a healthy human being who doesn't have Parkinson's, you're able to like hold your hand relatively still, but with Parkinson's, then your hand like shakes to an extent, right? So yeah, you can see that in specifically in like the holding position, you see a lot of like jittery movements in all axes, and that's representative of just how, I guess, sensitive accelerometers are when it comes to like detecting movement and trying to read like the forces in all directions. And because of this like jittery noise, it can cause inaccurate readings, especially if you're like constantly collecting information, and that can interfere with our feedback loop eventually. And so the verdict when it comes to accelerometers is, as we mentioned earlier, it provides like a three-dimensional vector of like where the orientation of the device itself, like where it's pointing, and it calculates that using net acceleration of movement, and it's especially useful with low frequency movements, so non-jittery movements, where such as like slowly lifting something, or as your quadcopter, I guess in the scope of a quadcopter, like when it's slowly taking off, when it's like, I guess, what's the term, like yaw, where it's like turning to the, like hovering to the left or hovering to the right. So smooth movements, right? And it can actually record these in relatively high detail. But when it comes to high frequency movements, really all those like really jittery readings will introduce a lot of noise into the system, and our feedback loop will struggle to handle that.
No, but yes. Yes. I was going to say.
And I think this is yours, Larry?
Like he's an average player.
Yeah, I added this slide. This
Okay.
slide is just for you to see what the
Yeah.
difference is. And basically, accelerometer is really good at low frequencies because no matter how you move it, gravity won't change in the long term. Gyroscope is very good at high frequencies because it can measure sudden changes in angle, and it's directly measuring this derivative of it. And then drift causes it so that for over a long time, you end up getting a gyroscopic drift. Yeah.
So, as you have probably guessed, the fact that we have both a, I guess since our IMU has both like a gyroscope and an accelerometer, you can assume that, you know, we're going to use both of them, right? So how are we going to combine the two? Excellent. Yeah. Okay. So if you guys have taken EE 102, this will be like a quick review. So traditionally, when we look at things, it's in like the time domain, right? So it's like some variable with respect to time. And that's how like you've typically graphed like sine, cosine functions, right? Time versus amplitude. But in the frequency domain, you can express some like sinusoidal signal, or honestly any signal, into a combination of frequencies and intensities. So for example, on the right, you can see that, oh, this is a relatively high frequency signal, and it's like a constant frequency with amplitude, let's just say Y. So in the frequency domain, you see that it's this specific frequency with amplitude Y. And same with the one in the middle, it's slightly smaller frequency. So on the frequency domain, it's farther to the left with the same amplitude, right? But in the third example, it's not like a traditional sinusoid. It's like a combination of two of them. And if you break that down into the frequency domain, you can see that it's actually the sum of two signals of of two different frequencies with the same amplitude. And what they allow you to do is as in the example on the right, is you can then express like very complex signals into their specific frequencies, into a breakdown of their frequencies. And that kind of brings us to filters, where we take an input signal and only keep the desired frequency components that we want. So we mentioned earlier that for an accelerometer, it doesn't do very well with like high frequency movements. So we would want to filter that out and instead use the accelerometer for low frequency signals. And on the contrary, we can't just ignore all of the high frequency components. So that's where our gyroscope comes in. So we'll be using both of them in tandem to compute the orientation of our quadcopter. So this, yeah, and that brings us to filters. So we have, in an ideal situation, you'll learn that like impedance is for a capacitor is equal to negative J over WC. You'll learn that in EE10, fantastic class. And at low frequencies, you'll realize that capacitors behave differently at certain frequencies, which is like the real world case, unlike ideal cases. But so at low frequencies, you can see that impedance will actually approach infinity. So current will like pass through, And at high frequencies, it'll pass like through the circuit to the circuit. But at high frequencies, impedance will approach 0. So current will pass through the capacitor to ground. So like it won't be able to filter it out. And so that's why we use multiple capacitors, because in the real world, capacitors also have inductive and resistive elements. So earlier we mentioned that like capacitor impedance is like negative J over WC, but for an inductor, it's JWL. And then resistance is just resistance. And so this is why we use decoupling capacitors to filter out a certain range of frequencies called a band stop filter. And you can see that in the middle, I guess the top graph, where it's called a band stop response. So these devices in the frequency domain will actually, if you convolute the two signals together, where like it's more or less like kind of combining, like passing a signal through this device, you'll see that it'll filter out all of those like frequencies in the middle. And then to the left and right of that band stop region is the pass band. So the frequencies that are actually allowed through past the device. And so the more capacitors we use in parallel, we'll be able to filter out more frequency ranges. And in our case, because we're using two different devices, the accelerometer and gyroscope, for different frequency readings, then we'll have to implement a complementary filter. So at low frequencies, I mentioned earlier that we'll want to use the accelerometer, and at higher frequencies, we'll want to use the gyroscope. And so what our complementary filter does is we'll have two separate filters that passes information that passes information to each of the devices. So we'll have one filter that filters that is a low pass for the accelerometer, so low frequency into the accelerometer, and then that's a funny joke. And then we'll pass the high frequency information into the gyroscope for a high pass to read the high frequency information using a high pass filter into the gyroscope. And so we pass the low frequency readings and the high pass readings into like into an adder, and then we'll essentially be like adding all of the readings into one. So we'll have one whole reading from that combines the accelerometer and gyroscope readings. Yes. If I had $1 for every pixel in that image, I would have 87 cents. Nice, Julian. But yeah, so for our implementation, we're going to be we'll be implementing the low and high pass filter using software in Cube IDE. So we'll be walking you guys through that. But as I mentioned earlier, we'll be taking the low pass data from the accelerometer, add it with the high pass data from the gyroscope, and that'll be like a whole reading that combines all of the information that we've collected. And as we collect that information, we'll be updating the orientation vector that we'll be tracking within the MCU itself using the combine and filter data from both sensors. Sorry. And this is actually a really good example of demonstrating like where the accelerometer and gyroscope have their like limitations and strengths. So if you look at the high frequency impact of the readings, you'll see in blue is the accelerometer readings, right? So you'll see with sudden movements, you'll get these like really random high amplitude spikes in your readings, right? And that's really not desired. But with your gyroscope, then you'll see over time, the gyroscope reference vector, it slowly like drops down with respect to like the angle. So highlighted in red after I guess 1021 milliseconds, then the gyroscope is virtually unusable. Like the raw readings from the gyroscope are unusable at that point. So, and then if you look at the low frequency towards the beginning of the plot, then you'll see that the accelerometer is relatively reliable in conjunction with the green filtered readings. And the gyroscope is at that point then filtered out, and we can just use the accelerometer readings. So The green line is a representation of what our combined reading will be if we performed the high pass filter for the accelerometer combined with low pass filter data from the gyroscope. And we'll be getting like the green line.
Okay, any questions regarding the content? I know it's quite a abstract concept, but we can definitely help clear things up if you guys have questions. Nope, then okay. Okay, so you guys will have one lab for the rest of this quarter, which will be the next coming 4-ish weeks. You're basically going to be using CubeIDE, which is a programming platform to program your Nucleo board. Your Nucleo is basically like an Arduino. It's just, but in a sense, it's very similar to our custom PCBs, because before, if you've used an Arduino before, you know, they have like certain pins that have certain functions. And you know, if you realize that MCUs have the exact same results, and basically what an Arduino does is it kind of has, other than some extra things, connects the MCU pins out to breakout pins that you can use. Of course, there's some other stuff, but it's basically another custom PCB. So you're going to have to look at the data sheet to know how your Nucleo is connected and how you're going to program it. And not only that, this will help you pretty much directly program your quadcopters in the future. So some documents that you'll need to get started on. I've been really lazy about the website because it's kind of a pain to upload all the time. I might edit it again, but I wouldn't trust it, to be honest. I just uploaded it at the beginning. But the documents that you will need to get started for this, that we will post on Facebook this time, along with the lecture, is 1, the lab spec, obviously. 2, the CubeIDE tutorial. This will teach you how to run through like a program and get started on your Nucleo. And then we pass AP leads, plus this time I also wrote some stuff, have some library files for you, as well as skeleton code for you to start working on it. And in fact, the CubeIDE and the lab files are all linked in the lab spec at the very beginning. So you really just need a lab spec, but this is what you'll be looking for to get started. For the rest of the quarter, this is your lab. So part 1, you're basically trying to read your gyroscope's raw data. Gyroscope and accelerometer, sorry, not just gyroscope. Gyroscope and accelerometer raw data. And specifically, if you know about I2C, it's implementing read and write sequences to your boards, initializing your parameters for your IMU so you can actually make use of the data you can get. Part 2 will be taking the accelerometer data and the gyroscope data to create 2 representations of true up, because it's not as simple as just getting the data and then calling it a day. It might be with the accelerometer, because that's the easiest one, but gyroscope, you might need to do some like numeric integration and whatnot to do that. So then after that, you'll take these 2 representations and create a complementary filter to get a much better version of what you have for true up. Afterwards, you would send that data to your computer through UART to this orientation visualization software that was written by one of the one of the original AP leads, who is kind of a crazy genius software.
Mega big brain.
Yeah, mega big brain software. But it helps you, it basically creates a vector using the data you output to your computer through serial, and it helps you visualize 3D graphs.
Yeah.
Yep.
One additional thing is that the development boards that we shipped out actually have an identical MCU to the one that you guys are using on your custom PCBs. So that should help the code translate a lot better. So you don't need to reassign too many of the pins and stuff for when you actually assemble your aircopter.
Yeah. You will, yeah, it's pretty much going to be the exact code that you put on, except for one small detail that I kind of don't want to talk about right now because it's a little bit confusing. But it will get over that when we get to that point. Cool. Any questions? Great. There's no questions. I have a feeling that there's no questions because people are just confused. Is that true? Am I right? Someone want to type in the chat?
Somewhat.
True. 50-50, yeah. Well,
Speak now or forever hold your
yeah,
peace.
speak now or forever hold your peace, because we might be able to clear things up really quickly.
Or you can just message us in your team chats. That works too.
Yeah, but also it's just like, oh, I don't want to go over it like with everybody, you know, I'd rather everyone hear it. How are we going to do the filters in software? If so, how? Yes, it's going to be in software. So the example Aaron talked about for the capacitors and whatnot, this is for this is we've implemented decoupling capacitors. He's using this as an example to tell you like an example of what a filter might look like.
Yeah,
In
it's
our
like
cases,
a physical
we get,
filter, a hardware filter.
digital values. The way that we implement in software is, it's in the lab spec. I don't want to really talk about it, but you basically have a filter. You basically add the two things together with certain coefficients. Let's just say that by differentiating your gyroscope's orientation of true up, you can get an idea of the high frequencies will get amplified, right? Because if you have a cosine, then it's like times omega
Times
whatnot.
a lot, times frequency.
But yeah, but then if you have like a flat value, as in your thing's not moving, then it would be 0. So the effect of it is dependent on its frequency in that sense. That's kind of what you do. You don't actually take your gyroscope data, form the true up, and then add that in through some way. You just take the velocity data itself.
Yeah, you're kind of like extracting information from the gyroscope data. You're like extracting quote unquote frequencies to an extent.
Yeah, we have the exact. It's actually surprisingly like a very simple equation. But yeah, we have that in the lab spec. That's just like the general idea of what we're doing though. Anything else? Okay, if we have no questions, then we're good.